Hello, everyone. Dr. White here with a short demonstration involving an app you can play with in RStudio. What we're going to do is learn about how skewness of a distribution of a numerical variable can affect the mean and the median, and also see how you can detect skewness just by looking at a box plot if you happen not to have access to, like a density curve. So sorry for showing you this RStudio. This is my local installation, so it doesn't look a lot like the server you've seen in other screencasts. But you can do the same thing on the server. Let's see. What you want to do is make sure that you have attached a package, tigerstats. Here, I'm going to make sure that things are a little bigger here so you can hear me here in the console. I'm saying library tigerstats. That's going to get you access to the function that you need to call, which is called skewer, S-K-E-W-E-R, and there it comes up in code completion. I press it. It's got the parentheses, so it's like all ready to run a function for us. And I press enter. And you get a picture, you get a graph coming up in your plot window. And I think this time it might be a good idea to enlarge it. So I'm going to just like make it big on to the left and right, and make it big going up and down. And let's even go further. And it kind of resizes itself. And this is a special plot. You can interact with it. Do you see that little cog up in the upper left-hand corner where my mouse is hovering? And the tooltip says, show the manipulator for this plot. And so I click on it. All right, now let's take a look at what we've got here. In the plot window, on the left is a histogram for some random data. And looking at that histogram, we can see that the distribution of the data is unimodal and roughly symmetric. The histogram is kind of a mirror image of itself around this vertical line I'm drawing in the middle of the data. Looking over into the console, right after you ran the command skewer, it came out and said median equals something and mean equals something. Now your results are going to vary, but they're going to be similar to mine. It's all random data, but there's a similar pattern to it. My median is 50.31. My mean is 50.32. You too are going to have a mean and a median somewhere around 50 when you try this out. Now that's how it should be. When a numerical distribution is symmetric, the mean and the median will be really close to identical. You can also look at this distribution with a density curve. If you go to the manipulator to the little button, Show Population Density Curve, you can click it and the density curve comes up and it looks like really close to normal. And this is what's going on here. This data that I've pulled out randomly is pulled out from a population where the distribution is exactly this symmetric bell-shaped distribution that you just saw. Okay. Now over here on the right, where I'm waving my mouse, is a Violin plot of that same random data picked from that population. And so you'll notice the distribution, the Violin, is basically a density curve for the data here on top with a mirroring density curve for the same data on the bottom. And so you're seeing that most of the values are somewhere here in the middle because that's where the Violin is fat. Now we've also got a box plot drawn for the same data. And you've got at the beginning of the box is where the first quartile of the data is, and at the end of the box is where the third quartile is, so kind of roughly a little more than 40 and a little less than 60 for the first and third quartiles. The middle half of the data is between those two. You've got two hinges, a left hinge and a right hinge. This is basically the bottom 25% of the data, and this hinge is the top 25% of the data, except for a few outliers that are plotted here individually, here and here. Okay, so that's how a box plot looks when the distribution is symmetric. So what I'm going to do now is play with the population. Instead of a totally symmetric population, as indicated by this little density curve here where I'm waving my mouse, let's make one that's a little bit skewy. So I'm going to move this little slider over. And now you see that for the density curve for the population, there's just a little bit more tail to the density curve over here on the right than to the left. So it's a little bit skewed to the right towards higher values for your x. So not surprisingly, the random data that we picked from the population, it follows that population curve kind of okay. That histogram is showing that. And it also is a little bit right skewed. Check out the mean and the median now. The median is at 43.76. The mean is at 44.01. That's so the mean is a little bit bigger than the median, not a whole lot, just a little bit bigger. It's being dragged a tiny bit of the way towards the tail, whereas the median is still trying to hit the middle value. Over here with the density, with the Violin plot and the box plot, again, the Violin plot is showing a bit more tail off to the higher values. You can also see that in the box plot. This hinge here, the upper one, is a little longer than this hinge here, the lower one, especially if you kind of throw in those outliers to make that tail. But it's not a really strong effect. Let's make this curve more skewy. How about go halfway up? Now you really start to see the population is noticeably skewed to the right now. And so the random data that goes along with it is also noticeably skewed to the right. And that effect is really showing up here in the box plot. The lower hinge is shorter than the left hinge, plus all those other points that got plotted as outliers. So that right hinge along with those outliers is really showing you that there would be a right tail to this distribution. If you were only looking at the box plot, you could tell this data is right skewed. That's one of the things box plots are really good at doing, is they can show you skewness. Let's make the distribution like as skewy as we can get it by pulling the slider up to a 1. And so now it's like super skewy. Look at that. It's basically all tail headed to the right. Look at the box plot. The lower hinge, that's the lower 25% of the data, all crammed up into that tiny little region for x. And the upper 25% plus those outliers, that's kind of really spread apart. It's showing you that tail. And look at the difference between the median and the mean. The median's at 6.23 and the mean is at 8.98. It's like 1.5 times as big as the median. The mean has really been dragged up towards that tail. The more skewed the data is in one direction, the more the mean is going to be dragged away from the median towards that skewness. And the more the box plot is going to show you that skewness, especially by an imbalance between its hinges. Whichever hinge is way longer is where the skewness is. And also, if there's a lot of skewness, you'll tend to find a whole bunch of things classed as outliers that kind of extend that hinge, as it were. So we finished looking at this. I'm going to go ahead and resize my screen, which I hope I can do. It's yeah, there we go. You can play with the boundaries, and you should do the same if you've enlarged your plot window. Get it back to something smaller, and you're done playing with the app, so you can look back in your files if you want. Okay, lesson over. What we've learned is two things mainly. That the more skewed a distribution is, the more the mean is going to be dragged towards the skewness, and it'll differ from the median. Second thing we've learned is that you can detect the skewness with a box plot. The skewness is going to be in the direction where the hinge is a lot wider. That's it for now. See you another time.